I know the next lesson that I'm going to teach you is going to be difficult for you to understand the first time we go through it. So you really need to write down questions and focus your attention on things you don't get so that when you get to class tomorrow or after you've watched these notes, you really start talking to me about what you don't get. Because the idea of logarithms is not the easiest thing to get at first. In fact, some kids really struggle with it, but once you start dealing with it enough, it will make sense to you, and you will understand it. Logarithm functions are inverses. What are they inverses of? They're inverses of exponential functions. So that's why we're talking about them right now. You are very used to squares and square roots. You are used to addition and subtraction. Those are things which are inverse operations of each other. Multiplication and division. Well, we need to talk about log functions, but really to kind of get the flavor of what a log is, you kind of ought to understand how exponential scales work. For instance, you are extremely used to the linear scale, such as temperature. The linear scale for temperature, let's say on the Fahrenheit scale, 50 degrees, 51 degrees, 52 degrees, 53 degrees, 54 degrees. That's linear. Each movement up a degree is almost not even noticeable. So if you were to ask me that whether it was 50 or 51 degrees outside, I wouldn't be able to distinguish the difference between those two things. In fact, if you said, how could you compare, or what's the difference between 54 and 50 degrees, we would subtract them, because on a linear scale, everything is based upon addition and subtraction. So comparing those two, I would just need to subtract. Well, the exponential scale is different. The Richter scale, which we use as a measurement for our earthquakes, is based upon exponents. These numbers 0, 1, 2, 3, 4, 5, 6 are values on the Richter scale, but what they correspond to, let me zoom in a little bit here. The values, it's the energy released times 30, or the energy released times 30 squared, and an energy released times 30 to the third, and 30 to the fourth, 30 to the fifth, 30 to the sixth. In other words, these values are exponents. Now, let's understand what that means. When I ask you to compare the amounts of two different earthquakes, one being magnitude 5.5 and one being magnitude 4.5, because it's an exponential relationship, I take the 30 to the 5.5 and I divide it by 30 to the 4.5. And what am I supposed to do with these exponents? I'm supposed to subtract them. And we know that if we subtract them, we get 1 for the exponent. So 30 to the first. In other words, it's 30 times stronger. Now, I'm not going to notice a 4-degree temperature difference outside. But I would think I would notice that an earthquake was 30 times as strong as a previous earthquake. That seems to me to be a great difference. So that's something you've got to get used to, is understanding that on the scale, linear scales are different than exponential scales. These values as exponents are extremely different than just a linear dimension. Okay, so really you've done example 1. Now let's move on to example 2, understanding the difference between the exponential form and the logarithm form. Now, we all know that 2 to the third power is equal to 8. The logarithm form of the same exact statement. So these two things are the same, but in a different form. the log base 2 of 8 equals 3. Log base 2, this is the base, this is the exponent. What it equals is called the argument. So the base of the logarithm is written on the log side as a subscript. You notice that I've written a smaller value kind of below the level of the line where the log and 8 sit. Over here's your exponent. And right here is your argument. So we can change things back and forth. So if you ask me to change something that's log base 3 of 27 equals 3, now one thing I like to do is I like to I use an arrow situation or just as a way to kind of help me understand that I start with the base, I move around to the exponent, and that equals the argument 27. 3 to the third power equals 27. So these two things mean the same thing. They're just in different forms. You will be expected to be able to go back and forth between these two forms. If you can't do this, you will really miss out on a lot of things, because in a lot of situations we need to solve equations and we need to use the other form. I'm always going to say to you, if you can't solve it in its exponential form, change it to its log form. If you can't solve it in its log form, change it back to its exponential form. So just don't think that you can get away from this. You need to be able to go back and forth very easily. So I guess the moral of the story is that logarithms are just exponents. Log base b of y equals x is the same as b to the x power equals y. These two things are the same. Obviously, one of these is solved for y, and one of them is solved for x. So each form can come in very handy depending upon the situation. Now, another way to look at this is that a logarithm is the inverse operation of raising something to a power. It allows us to solve for exponents. That's critical. We need to be able to solve for exponents. Now, I'm not going to let you use a calculator. This is no calculator on this kind of question. Period. No calculator. It says evaluate log base 8 of 16. Now, I know it has to be equal to some number, so I'm going to write equals x. The book does not like to do that, but you should do this. Every single time you should write equals x, because you know it has to be equal to a value. Now, I can't solve it in that form. I don't know what to do with it, so I need to change it to its exponential form. So 8 to the x power equals 16. Now, if you know how to write 16 as a power of 8, I'm really happy for you. But I doubt that any of you really are able to do that at this very moment. But I am pretty confident that most of you know or can see that there is a common base to both sides. What base is in common to 8 and 16? Yes, the answer is 2. So I'm going to rewrite 8 as a power of 2. 8 is 2 to the third. 16 is 2 to the fourth. Yes, you should know some of your integer powers. And we'll take a look at which ones you'll need to know for when we get into a testing situation, especially since some of these problems you will not be using a calculator on. Now, what do the basic laws of exponential functions allow me to do? When you have the power of a power, yes, we need to multiply those exponents together. Folks, take a look at it. If the left side equals the right side, which this little symbol in the middle guarantees that they do, and I notice also that this base and this base are the same, what does that tell me about these exponents? It tells me that these exponents have to be equal. So 3x has to be equal to 4. That would mean x is equal to 4/3. I know that that wouldn't have been very obvious to you, so you're probably going to have to practice more of those. Let's do a few more of them. So I know it equals x, even it has to equal something, even though the book didn't tell me what it is. So rewrite it. 64 to the x power equals 1/32. Now, once again, I don't know how to rewrite 1/32 as a power of 64. If I did that, that'd be an easy way to solve this problem, but I don't. So I need to rewrite it in a common base. And the common base between 64 and 32 is also 2. So 64 is 2 to the 6th power. 32 is 2 to the 5th power. Now, what do I do in order to get this base to flip over or to move this to the top? That's right, negative exponents. So what am I allowed to do with the 6 and the x? Yes, multiply them together. So if the left side equals the right side and the bases are the same, what do you know about the exponents? Sure, you know that 6x equals negative 5. So x must be negative 5/6. Okay, let's practice again. It's got to be equal to something. Rewrite it into its exponential form. 9 to the x equals 27. What's the common base? This time it's not 2, it is 3. So we have 3 squared to the x and 3 to the 3rd. Well, what are we allowed to do with these? We can multiply them together. If the left side equals the right side and the bases are the same, what do we know about the exponents? Well, they have to be equal. So this one has to be equal to that one. So 2x equals 3. X must be 3/2. That one wasn't too bad. This one will be even easier. Rewrite it into its exponential form. 10 to the x power equals 100. You know what? I do know how to write 100 as a power of 10, so that's what I'm going to do. This is 10 squared. So guess what? If the left side equals the right side and the bases are the same, I know that the exponents are also. So that was an easy one to solve. X must be 2. Now, the term common logs are base 10. So we stop writing the base. If this becomes this. In other words, when you don't see a base written in there, you know you can always assume that it is base 10. Always, always, always. Just like in the next example, example 4. Did you know that pH and hydrogen ion concentration have a logarithmic exponential type relationship? No, this is not a formula or equation you have to memorize. If you need it on a test or quiz, I will give it to you. So let's suppose that the pH is 2.3. What's the hydrogen ion concentration? Okay, so I plug my 2.3 into the equation. Now, before you can change it from its log form to its exponential form, you need to get the logarithm by itself. So the first thing I'm going to do is I'm going to divide by -1, making this -2.3 equals log of the hydrogen ion concentration. Now, based on what I told you a few seconds ago, I don't see a base right here, so I know when I'm going to rewrite this that the base I'm starting with is 10. So 10 to the -2.3 power is equal to the hydrogen ion concentration. So 10 caret -2.3, 0.005 approximately. Now, what do log functions look like on the graph? I want you to start by remembering what your exponential growth function looks like, y equals 2 to the x. You remember when you don't see the y intercept in there, do you remember what it is? Sure, it's a 1. And we know that the basic looking picture looks like this. It's what we want our money to do. Now, what happens when we switch x and y? Well, let's see here. Y equals 2 to the x becomes x equals 2 to the y. And then solve for y. Right? This sounds like the process of finding an inverse. Well, in order to solve that for y, I need to change it to its log form. So the base is 2. The argument is x. The exponent that it equals is y. Right? Logarithms are just exponents. So there it is. Y equals, you can write it the other way if you want. Y equals log base 2 of x. That's the inverse function. Now, what did we do? We switched x and y. We know what that means. Remember, when you switch x and y, something happens to all the points on the graph. We talked about reflecting across a particular line. What line is it? That's right. It's the line y equals x. That's the line you get to reflect across. So imagine what your picture would look like if you take all of those points and you reflect them across that line. Well, I'll show you what it looks like. Now remember, back on my old graph, the point 0, 1 was on the graph. And y equals 0 was my asymptote. Remember that stuff? Well, when you switch x and y, now x equals 0 is your asymptote. And 1, 0 is on my graph. Because remember, we switched x and y. And remember that line y equals x is, well, you get a graph that looks like this. Every one of your log functions looks something like that. Even if the bases are different. If the bases are different, it's slightly different looking, but not a lot. They all have the same basic shape, the same domain and range, which I'll talk about to you in a second. By the way, what do you think the domain is? By looking at the picture, I can tell that it's all x values to the right of the asymptote, so that'd be x values greater than 0. If you put equal to on there, then I know that you don't understand what the asymptote is because you're not allowed to touch that line. Well, what about the range of values? Well, this thing gradually gets bigger and bigger and bigger, and it'll hit every y value going up this way. Now, it might take a while to get out there and get a high value, but here it's going to go down really fast, really fast. So I'm going to cover every real number in the universe. So you've got your x equals 0 for your new asymptote, and your domain and your range. We are going to be skipping example 6 on translating log functions. So when you see those problems in the book, don't need to worry about those questions because we're skipping those. See you in class.